We present our work, Syntactically Guided Generative Embeddings for Zero-Shot Skeleton Action Recognition from CVIT at IIIT Hyderabad, India. Skeleton action recognition is the task of recognizing human activity given only a skeletal representation. It is advantageous over RGB action recognition since it is a compact, privacy-preserving representation. In the task of traditional skeleton action recognition, the data from all of the classes is split into the training and testing set. Therefore, the splits formed contain samples from all of the classes present in the dataset. The action recognition model is trained on the training set formed. Once the model is trained, its performance is evaluated by making it recognize actions from the test set, which was not present during the training phase. A variety of approaches exist for skeleton action recognition. Unsurprisingly, recent approaches use deep neural networks for this task. They also managed to attain exceptional results on the NTU120 dataset. However, a major issue with these approaches is that they are prone to overfitting and also fail to generalize on classes outside the training set. Keeping these drawbacks in mind, we turn to the task of zero-shot skeleton action recognition. In contrast to traditional action recognition, in this problem, the classes are divided into two sets, seen and unseen classes. All the samples from the seen classes form the training set, whereas the unseen classes form the test set. The data from the training set, that is, the seen classes, are used to train the action recognition model. The model is then tested from samples from the test set, which consists of unseen classes. Most zero-shot learning skeleton action recognition techniques use a feature extractor module to extract useful information from the given skeleton representation. The class labels are also encoded using a language encoder. The two embeddings hence obtained are then fed to a zero-shot action recognition model which learns to classify a given skeletal sequence. ZSL approaches achieve generalization by exploiting some extra semantic relationship among the classes, typically from the natural language embeddings of the class names. However, such techniques ignore the syntactical information present in the parts of speech of the class name. Typically, ZSL or GZSL approaches can largely be segregated into two major themes. The first one are mapping-based approaches, where the data from the visual stream and the language stream is aligned after being projected to a common embedding space. The others are generative approaches, wherein the unseen samples or features from the unseen samples are generated using either generative adversarial networks or variational autoencoders, and later a classifier is learned on top of them. However, as shown before, all these approaches ignore the syntactical or parts of speech information encapsulated within the data from the language stream. We've already identified one weakness of existing architectures. Another common problem is overfitting to the seen classes, which hurts the model's performance in the more realistic, generalized zero-shot learning setting, where the test set contains samples from both seen and the unseen classes. Keeping these weaknesses in mind, we propose Synesse, an approach that generates embeddings that capture the syntactical information that other methods fail to harness. In our approach, the embedding for the skeleton action is generated by an action sequence encoder. However, in our approach, Synesse, we divide the class labels into the different parts of speech. Here, we divide the class label into two parts of speech. One is the verb, which is put on, and the other is the noun, which is shoe. These parts of speech are then individually encoded to form embeddings for each of the parts of speech. The three embeddings hence generated are then fed to our generative multimodal alignment module. Taking a closer look into the module, we see that it consists of a variational autoencoder for each of the three embeddings. The encoders of the three VAEs generate a latent embedding for each of the three inputs. The latent embedding generated by the skeleton action encoder is split into two parts, representing the skeletal verb and the skeletal noun embeddings. Also, the embeddings generated by the verb encoder and the noun encoder are concatenated. As we go through the various losses that the module uses, we first pay attention to the reconstruction loss, which is used to reconstruct the input by the decoders of each of the VAEs. The split skeletal verb embedding is reconstructed by the verb decoder, whereas the split skeletal noun embedding is reconstructed by the noun decoder. The concatenated parts of speech embedding is reconstructed by the skeleton decoder. The losses introduced by all of these reconstructions are minimized, thus forming the generative multimodal alignment module of Synesse. In order to mitigate the low unseen accuracy in the generalized zero-shot problem, a seen classes classifier is used to generate a probability vector for a given sample. Another unseen class classifier also generates a probability vector for the sample. These probability vectors are then provided to Synesse's gating module. A look into the gating module shows that it uses the elegant gating approach by Adsman et al. In their paper Adaptive Confidence Smoothing for Generalized Zero-Shot Learning. Essentially, we learn a binary classifier which distinguishes between seen and unseen classes. We conduct our experiments on the NTU60 and the NTU120 datasets. For the NTU60 dataset, we create two splits. One is the 55 by 5 split, which demarcates 5 classes as unseen, and a larger 48 by 12 split, which chooses 12 classes randomly as the unseen classes. In a similar fashion, a 110 by 10 split is made for the NT120 dataset, which contains 10 unseen classes, and a larger 96 by 24 split, which contains 24 unseen classes. In order to evaluate Synesse's performance, we choose 3 strong baselines for experimentation. The first baseline, revise, aims to align the latent embeddings realized via autoencoders using a maximum mean discrepancy criterion. However, they neither use generative embeddings nor do they instill part of speech awareness in their embeddings. Our second baseline, JPOS, attempts to learn parts of speech-aware embeddings of word-to-vec representations for video retrieval tasks. It learns a series of progressively refined embeddings under inter- or intramodal constraints in a discriminative setting. While JPOS does learn part of speech-aware embeddings, they still don't learn them in a generative setting. Our third and final baseline is CATO-VAE, which learns a generative latent space under a cross-aligned and distribution-aligned objective. However, the learned embedding spaces are still not parts of speech-aware. Here, we position our work with respect to the previous art in terms of the qualities of the learned embedding space. As seen in the table, revised JPOS and CATO-VAE all are missing either one or both of the features that are present in Synesse's learned embedding space. We evaluate the performance of Synesse as well as the baselines on both the splits of the NTU60 and the NTU120 dataset. Right off the bat, we observe that the generative approaches perform far better than the non-generative ones. Unsurprisingly, as the number of unseen classes increase, the accuracy for all of the models decreases. However, Synesse's decrease in performance is far more graceful than the other baselines. For the 5 unseen classes split of the NTU60 dataset, our approach Synesse comes second to CataVA. However, as we move on to the more challenging 12 unseen classes split, the improvements brought in by Synesse become very apparent. Synesse also performs significantly better for both the splits of the NT120 dataset. In order to highlight the best design choices, we perform various ablations for zero-shot learning. We experiment by changing the language embeddings used, the visual features, size of the latent dimensions, and the number of latent features. The results in the first 2 rows show that using sentence BERT and forest shift GCN serve as the optimal choices for the language and visual embeddings respectively. The next 2 rows show that both an increase and a decrease in the size of the latent embeddings causes a drop in the accuracy. Finally, the number of latent features used for training the zero-shot learning classifier also slightly affect the accuracy. Further, we evaluate the performance of all of the models for the task of generalized zero-shot learning. Following standard convention, we report the seen accuracy, the unseen accuracy, and the harmonic mean. A better accuracy on the harmonic scale means better performance as far as the generalized zero-shot learning task is concerned. Following the trend from the zero-shot learning results, CataVA performs better in the 55 by 5 split of the NTU60 dataset. However, Synesse shows an improvement in performance in all of the other splits of the datasets. We perform ablation experiments within the generalized zero-shot learning setting as well. We first compare the hard gating strategy with the soft gating one proposed by Icip et al. Next, we train the gating module with temperature scaling the input probabilities. And finally, we compare with the traditional method for generalized zero-shot learning, that is, without the gating module present. We see that using a soft gating mechanism as described by Icip et al. Generally results in poorer unseen accuracies and hence a poor harmonic performance, with the exception of the 55 by 5 split. The third row shows the significance of temperature scaling the seen class probabilities before training the gating module. As expected, not performing temperature scaling results in a decrease in performance. Finally, as seen in the last row, the failure of traditional generalized zero-shot learning paradigms to recognize the unseen classes heavily emphasizes the need for the gating module. To conclude, we introduce Synesse, a compositional approach for infusing latent visual representations of skeleton-based human actions with syntactic information derived from corresponding textual descriptions. Also, our generative multimodal alignment block learns progressively refined generative embeddings aligned in a parts of speech specific manner under cross-modal reconstruction. Our gating module learns to classify between seen and unseen classes, thus allowing us to use separate, better performing classifiers. We present the first set of zero-shot skeleton action recognition results on the large-scale NTU60 and NTU120 datasets. Also, our results show that Synesse outperforms strong baselines for zero-shot learning and the more challenging generalized zero-shot learning setup. We would like to thank you very much for giving us your time. The source code and the pre-trained models for Synesse are available at the following GitHub repository.